And then, yeah.
Sure.
So then welcome to the second session this morning and the last session with talks. And the first talk in this session will be about certification for RoundingSat, the Pseudo-Boolean solver by Marc Vinyals.
Thanks, Yonder. Right, so let's start. First 5 minutes of the talk are going to be very boring because nothing happens. Last bit will be more interesting because there's this core guided logging, and that's a bit more tricky. So yeah, we want to do proof logging for RoundingSat. There's no reason to explain why, as in Dieter explained, because our solver is buggy and we want to find bugs. I mean, it's probably not that buggy, but still. The surprising thing was that while implementing proof logging, we didn't really find bugs. So there were bugs in logging itself, but not bugs in the solver. Anyway, yeah, so what does RoundingSat do? We've got this solver that does the Boolean reasoning, and it works with native general Pseudo-Boolean constraints, and we can use it both for decision and for optimization. And the other thing that it does is, well, it has this integration with linear programming. Good, so I'll start by talking about how do we log decision, and then we'll talk about optimization. So decision conflict analysis, there's not much to explain really, as in take Jakob's tutorial. He explained how we are going to get this conflict clause, and we'll have some reason clause, and then we will want to add them or resolve them in some way. So yeah, what we do is we take the reason constraint, we weaken it by remove some literals until the slack is 0. Then we divide, add to the conflict clause, keep going. So this we're going to log by using this reverse Polish notation. And the syntax is a bit clunky, but what this is saying is, take some clause, some constraint, weaken away this variable x1. So we're taking x1 multiplying by 3, and we're taking the opposite literal, so that weakens away x1. And if we want to weaken away x2, then not x2, then we add this variable x2, divide by 3, multiply by 2, up to something constraint.
Okay, Mark, one question. So if I compare it to these two stats, so I see a big difference, which might be motivated, but because in SAT so here you're kind of expressing every single step that you perform.
Yes, it's like doing resolution.
Yes. Whereas in SAT you do not have to to list every single resolution step, but you just write the output. So what is the motivation for this? So is it just impossible to do something similar in
Yeah, I think there's no good way in that you still have a RUP rule, so reverse unit propagation. So if you can derive a constraint that does follow from reverse unit propagation, you could in principle do that. But otherwise, it could be that your new constraint does not really do that. And then, I mean, in resolution, there's only one step that you can do, right? So if you know your clauses in the trail, you resolve them, you find it. In cutting planes, there are so many different things, right? Weakening, it's not clear what you should weaken. It's not clear which number you should divide by. So yeah, you really need to be precise, I think.
Yeah, well, I mean, my talk will be exactly about that point.
Yeah, so hopefully you'll have some ideas. And you're the very PV expert. Is there anything?
Yeah, but okay, so I guess we can discuss that in half an hour because I will have a sort of a provocative statement about that.
Good. Awesome. Great, and thanks for the question. Yeah, we'll talk about that. Good. So the other thing that RoundingSat does, besides this native Pseudo-Boolean conflict analysis, is sometimes it asks an LP, right? It gives the LP relaxation, and the LP tries to find invisibility. And if it finds invisibility, then we're happy. We can add a new constraint. So yeah, we just ask the solver for the Farkas multipliers, the LP solver, of course. And we find, okay, these are the multipliers. So we just add all these constraints that are getting multiplied together and say what the multipliers are. Here, I mean, an interesting bit is that because the solver works with fixed or, well, yeah, some bounded precision, but solver might be using larger precision. It might be that when you get the multipliers and you translate them that into integers, you might no longer get something that's infeasible. But yeah, that's something that the solver already detects. So when it goes to the logger, it's already in infinite precision, so there's no need to worry here. Right, then something else that the solver does, but we don't log, is sometimes the LP is going to be feasible, but the integer program is not going to be feasible. And then we can find cuts. We can cut the LP. And that's something that, so it's implemented using a mixed integer rounding cuts. It's not something that VPV supports natively. It can be done. If you use this redundancy rule, it's not a problem in that it's impossible to do it, but it would be somewhat slow. And still, it didn't make a big difference, and we did it. So we didn't implement that for the competition. We plan to implement it anytime soon, but it's not done yet. Again, it shouldn't be too big of a problem. It's just taking some coefficients, adding things together, dividing, or not dividing, applying this mirror rule, and should do that. Good. So now let's, that was everything that's related to decisions. Now let's talk about optimization. So what about optimization? There's two optimization modes that RoundingSat does. There's this solution improving, and there's score guided. So logging, solution improving, that's the first thing that we'll do. That's fairly easy again. When you find a solution, what you do is, okay, I'm going to tell the logger that I found a solution. So you have this very PV instruction, sol I, so for solution improving, and you say, okay, this is my solution. And now this tells the logger that you have derived a constraint saying that the objective should be strictly less than the solution you found. And again, it might not be a very good thing to do for the solver to add this thing unconditionally. But this is what we do right now. So this is what's getting logged. And then there's the lower bound part. So for the lower bound part, once we add an objective improving constraint that's too strong, then we know that we've got an infeasible problem. There's no solution, so we can just use the normal proof logging. We'll end up deriving a contradiction. So we can just use standard logging for that. There's nothing special that we need to do in this case. Right, so there's just recording solutions and finding contradiction. Now let's move to the core extraction bit, core guided bit. That's the most interesting. So what I'm going to tell you is essentially take this paper, Certified Core Guided MACSAT Solving, by a few members of the audience, even though a couple of them left, but still. And now, instead of having to do very complicated things because we've got CNF encoding and it's, so we need to encode constraints into CNF, and that's hard. We're just going to say, no, we don't really need to do anything. We just can work with linear constraints and be happy. Anyway, so let's start by how do we find the core? Again, so we find the core. So a core, first of all, is just some constraint that's falsified by the assumptions. And here it could really be any constraint. Could be, we work with cardinality constraints, probably because that's what MACSAT does. But again, we discussed this already that we could use more general constraints, that there's no reason why we have to stick to cardinality. But anyway, what we do is, so first we get this constraint through conflict analysis. So this is, again, nothing happens here. We use the standard conflict analysis login. And then once we're done with that, then we do have this constraint and we want to round it to cardinality. So now what we're going to take is some letters that we don't want, weaken them, and then divide by a large enough number so that we get cardinality. So again, not much going on. So we can extract a core reasonably easily. And then what we want to do with the core is to reformulate the objective. Right, so the idea is that we'll have some objective, we'll subtract the core from the objective and get a new objective. Piece of notation that I'll be using is this capital XS, that just means sum of variables xi in the set. It's very cumbersome when you have all these sums but they're only doing summing all the variables in a set, then it's distracting. So we'll be using this more compact notation. Anyway, so we've got a core, it's a cardinality constraint. So all that it's saying is, well, sum of the variables xi in the set S is at least d. That's our core, right? We know that that's impossible. And
so you assume that the core is always a cardinality constraint? Or?
Yes. Yeah.
Okay. But it doesn't need to be necessary.
Doesn't need to be. So right now it is. And for logging, we are also assuming this is what we know. Things shouldn't change much, but yeah, it's easier to do it this way.
So should the variables in S to be part of the objective function?
Yes, variables in S are all part of the objective because they will get subtracted from the objective. Right, and so the idea is that we've got this core all part of the objective. By the way, so on the first core, it's all part of the objective. On subsequent cores, it might be that we have variables from the objective, but also from previous cores that have now become the new objective. Good. So then what we do is add these new variables. So let's say YB, that's if and only if the core is larger than some bound. And again, this is not what we do, but conceptually, this is how we should think about it, right? That then we take our old objective, subtract this constraint, right? So which says that core variables that are greater than the minus core plus the subtract that from the original objective, get this reformulated objective. Right, and this expression delta k, if we think about it, it's always zero because it's saying just if the core, let's say it's d plus 3, if the true value of the core is d plus 3, then there's going to be 3 variables saying that there's the variable saying it's greater than d plus 1, variable that's saying it's greater than d plus 2, greater than d plus 3. So all these 3 are going to be 1, and then this whole expression is going to be 0. So if we take our core and add 0 objective and add 0 to it, we stay with the same objective. That's something we can do. We often multiply the core by some weight so that some variable, to make sure that at least one variable cancels. So usually what we're going to do is take these variables in the core, look at the one that has the smallest coefficient, then multiply the core by that coefficient so that one variable cancels. And hopefully more than that. Great. Yeah, so that's the conceptual idea. Now, the implementation is slightly different because we don't, I mean, the core could be huge. We might be introducing many variables here. So we don't want to do that. We're going to be introducing variables one by one. So this is what we do. We add variables lazily. So first we just say, well, maybe the core is not d, but it's also d plus 1. And if we find that it's d plus 1, then we'll worry about if it's d plus 2. But for now, let's just only worry about whether it's d or d plus 1. So then instead of having this expression saying that, yeah, this is what we are adding to the core, what we are really going to be adding to the core is only this. It's variables from d plus 1 up to some d plus I. And then we start by just saying y d plus 1 minus core plus that, right? And this is going to be measuring whether the core is d or d plus 1. And when we want to be higher, we'll add more variables. Yeah, so now we don't have that our objective is equal, our new objective is equal to the old objective, but we do have that our new objective is at most as large as the old objective. So if we got lower bounds for the new objective, then we also have lower bounds for the objective. So that's why we can, this reformulated objective is great for proving lower bounds. And on the other side, right, when we have a solution for the original variables, then we can also find upper bounds for the reformulated objective. Good. So then, since we will have not one core, but actually many cores, we will have some global constraint that's translating between original objective and reformulated objective. And that's going to be the sum for all cores of this reformulated constraint of a particular core multiplied by the weight. And what is always true is that when you go, so this constraint is always going to be at most 0. And this is something that we'll actually be able to derive. So we'll see how we log this constraint. It's something that's going to be useful. So 2 things. We can derive this thing, and it's going to be useful to derive other things. Do things make sense so far?
Maybe a conceptual question. I mean, if you start with yd plus 1, and when do you introduce yd plus 2? Once you have proven that yd plus 1 is 0, or?
Yeah. So you'll do that when you have another core.
Yes.
And that other core also uses, it has yd plus 1 in it.
So that it cancels out, and then you know that you have to take the next one.
Yeah.
Okay.
Okay. So yeah, that's then the plan, right? We're going to be adding these variables. And now let's see how we do this. So, right. One thing before that, I mentioned that, or in the previous slide, we saw that we had this lower bound on the core, right? So because of the assumptions, we had found that some of these variables must be at least d. Now, it's also going to be helpful to have an upper bound on the core. A very trivial upper bound is what we've got n variables. So, of course, some of these variables can be at most s, right? Nothing to see here. But sometimes we can get a better bound just by looking at the objective improving constraint. And so what you do is you take the objective improving constraint, which, by the way we get the objective improving constraint is by saying we've got a solution to the original objective. So here's the first instance when we have to use this reformatting constraint and say, okay, yes, I've got this upper bound for the original. I want an upper bound for the reformulated core, but I just need to add this constraint, and it happens. And then if we've got this reformatted objective, and we want to find an upper bound for our core, something we can do is say, okay, let's take all the variables that are outside of the core, weaken them, and now we'll get some sum, and it's over variables over s, and it's going to be less or equal than something. Now, if that something, that's what we're going to get. If that something u prime is now less than size of the core, now we've got an upper bound on the size of the core that's better than what we would get trivially. And we might want to use that. But the logging part of this is just, okay, we know how to go from original constraint to the ref constraint. And then weakening, we know how to weaken. And again, rounding to a cardinal constraint, that just means dividing. So good, this we know how to do. Great. So now we've got lower bounds and upper bounds in the core. Let's see how to introduce these reificated variables that say variable x d plus 1 is true if and only if the core is greater or equal than d plus 1. And again, so Jakob explained that in the tutorial, but what we want to find is some constraint in linear form that's equivalent to this semantic saying, well, yeah, if xs is greater or equal than d plus 1, then variable y d plus 1 is true. Right? And we'll also have a constraint in the opposite direction, but let's see how to log this one first. Good. So the constraint that we get is this something large multiplied by variable I y d plus 1 should be at least core minus d. Let's see for a moment that this should work, right? So if core is greater or equal than d plus 1, then this sum on the right-hand side is strictly positive, right? So then that forces the thing on the left-hand side to be positive. And because we're multiplying it by a large enough number, it's still satisfiable, even if the core is not d plus 1, but it's d plus 2 or something like that. Right? That's why we care about the upper bound, because if we've got a good upper bound, then we can multiply by something that's not too big. And in fact, the thing we need to multiply y d plus 1 by is the minimum of the size of the core, which was the trivial upper bound we had before, or the upper bound that we might have found from the objective. Good. So if we're convinced that that's what we want to derive, again, we'll do that in normalized form, right? We won't really write a constraint like this, but they should be equivalent. What we do is we're going to log this constraint using this redundant rule that Dieter talked us about. So this redundant rule, what does it do? Well, we can infer a new constraint if we can prove that our original set of constraints and the negation of that constraint implies our constraints and the new constraint, but once we after applying some substitution. And a substitution is just something, it's a mapping from literals, from variables rather, into 0, 1 or some other variable. So you can send x1 into 0, or you can send x1 into itself, or you can send x1 into not x3. Good thing is that for the kind of logging that we're doing, we don't need much of this complicated machinery. Things will be fairly obvious. So if we want to log, say, this constraint, it's something big multiplying y d plus 1 minus 4 greater or equal than minus d, then it's enough to apply this substitution y d plus 1 equals 1. Now let's see why that is true. So first, let's look at what happened to constraints that were already in the database. Right? So remember, what we want to do is show that we can infer this thing on the right-hand side from our left-hand side. So let's take a constraint that was in the original database. Now we have applied this substitution that sends y d plus 1 into 1. But original constraint didn't have that variable, so nothing changed. So of course, f implies f. That's nothing happened. Okay, so that's easy. Now the only thing that is different is that this new constraint that we are adding, that we also want to show that we can prove it. So what happens to this new constraint that we're adding? Well, we took this variable y d plus 1, we set it into 1. So that means that we now have c minus xs greater or equal than minus d. So that's what we get. Now, if we had just the trivial upper bound of the core, then this thing is size of s minus d. This is saying the core has size at most s. So it's just, of course, where you're adding s variables, it can have size, you can get at most s. Otherwise, well, what we get is this core upper bound that we derived last slide. We're going to get core less or equal than u prime. And that's something that we derived before. So since that's something that's, again, it will be in f, it's a constant that we've already derived, then that's something we can do. Things making sense up here? Great. So that was one direction of how we introduce this reified variable. The other direction is, well, yeah, the opposite. So now we want to say that if yd plus 1 is 1, then our core must be of size at least d plus 1. And again, we're going to use the redundancy rule, but now instead of replacing with y, instead of our substitution being yd plus 1 equals 1, it's going to be equal 0. And now again, we can go and check that all these conditions of the redundant rule, they're still satisfied. And so constantly in the database, still nothing changes. Now, the new constraint, again, if you set yd plus 1 to 0, it's easy to see that, yeah, that's actually our core. It's exactly that. Perfect. And an annoying bit is that, oh, but wait, we just added this reified constraint a moment ago, so we also have to check that one. And yeah, that, again, it's easy to see that if you negate that, so if you negate the new constraint, then you'll get that. Okay, so that's how we introduce a new variable. Yes, by the way, I mentioned that I would tell you how do we derive this constraint, saying that we can go from original objective to reformulated objective. So in fact, the first, this constraint is at most constraint. It's exactly equal to this reformulated constraint the first time that we derive it, but for at least for the first variable. But further steps are going to be different. And yeah, what happens when we add when we have to expand the core, right? So that would happen. We've got a new core. It contains variables in some old core. Then we have to introduce other variables. So now we won't have 1 anymore. We will have d plus something larger. The logging is, so introducing the reified variables is again essentially the same, not much changes. And the only trick is, well, we've got this objective reformatting constraint that we need to derive properly. So now that's getting derived by induction. So we take the reformatting constraint for the specific core. Turns out that if you do this trick, take that at the new reified constraint and divide by I. This happens to work. Very nifty trick that they had in their paper. So we can just use the same thing. And then from the objective reformatting constraint from each core, we can build the one that's the global, so a sum of all cores. And an annoying thing is that we can't just take the constraint, subtract the old core, and add the new one. That would not be sound. We cannot subtract. So we have to rebuild it from scratch every time. We could think of better ways to do this. I think it would be overkill because that's not something that happens very often. And good. I'm going to skip that question on core upper bounds. Last one more thing that we do is hardening. Again, that's something that is standard in MarcSat, in that if you've got a variable in the objective, and if setting that variable to 1 would give you a bound that's worse than what you already have, because we've got a lower bound, then we can immediately propagate that variable should be 0. And that's something that just by reverse unit propagation, it follows. So again, there's nothing we need to do here. We just say, yeah, this variable should be set to 0 by unit propagation, and we don't even want to think about why. Great. So yeah, to recap, right? What's done? So what can we do for RoundingSat? So conflict analysis is easy. LP infeasibility, that's done. Solution improving optimization, that's done. corrugated optimization is mostly done, except for a couple bits. And yeah, what we should do next is do this integrality cuts from LPs. Really complete all the couple of bits of corrugated optimizations that are missing. And so we've got some implementation of the constraint deletion that's a work in progress, should be done anytime soon. But so that's everything from me.
Are there any questions?
There's going to be questions for Daniel
Yes.
or from Daniel.
Well, if there are no questions, then yeah.
That's-
Thank you, Mark, again. And